So the first way in which I'll run this example is to free talk over the audio input interface and explore some concepts as if I was having a conversation with someone. There are some biotechnology concepts that in this talk or this meeting could be approached, such as nanoelectronics, genetic sequencing, fast sequencing devices, some home lab equipment for biotech enthusiasts, or for example space literature. Somebody could be studying geographic information systems or satellite communication protocols, downlinks using various radio bands from satellites, space telescopes, did I say that already? And other people might be focused on other science concepts such as LED displays or computer hardware, servers, and so on. Now I'm waiting for it to finish updating. There is a queue of requests that has to ingest all the responses, which are then rendered on the graph, and different concepts will be different connected components. I can then select some leaf nodes of one connected component to see what it's about and look at the tweets. Surely enough, this is about deep learning. These are all likes, tweets that I have previously liked. I can go to them and view the whole media content, such as images, metadata, neural networks. Of interest in this connected component could be the node of maximum degree. If I just select the 2, I'll realize, okay, there are some research articles. So in the later updates in my user interface, it's research nouns that I used seem to have been connected to machine learning tweets, just because the machine learning tweets usually reference papers, and there's usually academic people involved in this topic on Twitter. What are some of the other connected components? I see in orbit CFO sat, which talks about waves and spectra from various measurements done in the space domain. Scientists downlinked data from Parker Solar Probe, so not many matches on that side of things. The other connected component has discussions about sequencing. NextSeq 2000, sequenced using a nanopore. Good visualization in my opinion. After having performed the search, I want to expand some leaf nodes and see this connected component here. I want it to be connected in the end, or I want to enlarge it. So I'll right click the node, and this performs a similarity search with a multi-tiered graph construction algorithm, meaning first set of neighbors is then connected to a second set of neighbors, and a depth first expansion of the graph is done. Now if nothing happens, there are no results, but once I right click a valid node, there will be some renders, and in the end, when all the data is fetched, it will stop rendering and I'll have a new graph, and there is a high likelihood that this will be connected to the original graph. So let's explore some more. What happened, what was introduced in my old connected component, and of course Japanese cuisine, some old events from the news probably, let's see what we can select from here that could be of interest. One high degree node and some leaf nodes, and some mathematics, random graphs. This is the cover of a book that was in the recommended reading at my university, and it covers software engineering best practices and especially requirements engineering, topics in design thinking and problem understanding by using UML diagrams, such as the ones I'll be presenting next. While the first three diagrams I usually do on any project are the use case diagram, the class diagram, and the Dataflow diagram, I also do some analysis of user stories before starting and derive some main actors to use in a use case diagram. After I have my main actors and some stories that they might have in natural language, I go to make some use cases that are separate. Then I derive a generalization of an actor, such as the user in this diagram, and see which use cases apply to the more generalized or generic actors. This helps me understand the dependencies between the use cases better than if there was just one class of actor. Also, I have some highlighted use cases that are directly used by specialized actors and the relationship between them to see in terms of degree or the number of edges incoming and outgoing of each use case, which will be the most important ones. In the end, I realized that the solution I was developing was a vector similarity search or a sort of vector information retrieval system, because one of the main actors was an AI user and I had an important component named intelligent navigation, which was related to the graph database part of this project. Then I went on to my class diagram, where I was going to use inheritance. This means I had some specialized data types that I wanted to sort of downcast in a similar way in which a SIEM or event management system would work. The three data sources in this diagram are in the upper right corner, a data type corresponding to a data source, and an event stream can be something such as a message queue, which is by a composite relationship descriptive of a SIEM event, and that would include any event that I can gather from the streaming analytics like tweets, videos, and the metadata associated with them, which can be gathered via API requests. The Dataflow diagram shows me how I would use a data integration services system like SQL Server Integration Services to make some ETL pipelines in order to obtain all of the intermediate stages of data that could be used by any independent component of my application. I have some derived columns and derived tables. You can look up the syntax of these possible transformations using SSIS in this training article from Microsoft. Of course, some of those can be batch jobs, some of those can run based on events. At the end of the day, this is an OLAP system, online analytical processing. And of course, there is audio data in one of those intermediate stages, but the audio itself is not persisted, it's simply converted to text because of memory constraints. SQL Server Integration Services, as I was mentioning, has some visual or diagrammatic programming language where data flows can be modeled similar to Azure Data Factory. And this also supports Excel data sources and other formats you might have laying around in a legacy enterprise system, for example. The user stories table is very good for ideation or brainstorming. You write natural language descriptions of situations these actors from the use case diagram could be finding themselves in. In this example, I have some important stories that only use graph representations. So story 8 builds entity graphs, knowledge graphs, relatedness graphs. Of course, it has a size column with value 4. This column describes the difficulty or complexity of implementing the requirement which could address this user story. Second, in this case, it came after the requirements table is inspired by the stories table and assigns a priority to each independent component that can be implemented in the whole finished software product. And then the first traceability matrix, or user stories to requirements matrix, can be done, which is a sort of clustering system, and the traceability matrix can be used to visually identify which sets of requirements are the most important and should also inform the priorities given to each requirement. The next diagram is a general overview of the application architecture, including frameworks. Briefly, there are some data sources ingested into the Postgres database using Python. The Python backend is converted to independent Azure functions, and some of those are cognitive services or actual Docker containers or function endpoints using a machine learning model. The key thing to note about the choice of using Python for the backend is that the compute requirements for the application are small enough to be able to fall back to an Azure Functions project, which is very cost effective, but also offers the benefit of integrating the Python scripting into the data science lifecycle, where data analytics scripts and visualizations using Jupyter, for example, can be run to better understand the problem domain. The attached lifecycle screenshot is from a Microsoft resource. It shows that deployment is directly connected to the cloud architecture, cloud functions project, and the business understanding, data acquisition understanding, and modeling can be done using scripts which are then transformed into Python functions projects on Azure. So that is all I could come up with within the scope of one video. Thank you for watching. Please leave any thoughts about design choices and personal experience in the software industry in the comments. Tell me if you've interacted with vector databases before, for example, or you want another video on any particular topic related to cloud architecture or your approaches to designing user interfaces. Goodbye.